In this video, we present our work titled Autonomous Tracking for Volumetric Video Sequences, a system for enforcing spatiotemporal coherence for mesh sequences which is robust against noise, missing geometry, and also supports user edits. Many volumetric video systems generate data on a frame-by-frame basis, which often creates temporal inconsistencies by means of flickering and noise. This is especially true in small-scale studios where the number of sensors used is far smaller than the industry leaders. This leads to a greater number of occlusions and other geometry errors which can manifest as seen in these examples. Existing approaches address temporal coherence by using template priors which are tracked across the performance. However, the use of templates is limited to modest deformations and cannot model severe topology changes. Other approaches use a keyframe tracking strategy which allows for regular changes in topology, but existing systems do not address noisy sequences or support user editing. Our work provides a solution to keyframe tracking that improves upon the state of the art and extends applications towards entry-level content creation. In this work we present the following contributions. We present an automatic similarity-driven keyframe selection process based on spherical harmonics that minimizes keyframes and supports varying geometry and topology. A volume-based segmentation and registration method for robust tracking of volumetric sequences, and a tracking system that enables missing geometry recovery and realistic propagation of user edits. Our system takes as input a sequence of independent meshes which may contain spatiotemporal inconsistencies. We then automatically determine a keyframe-based tracking strategy to align keyframes to neighbor frames in a sequential cumulative manner. To perform this pairwise registration, we use a geometry-aware volumetric correspondence match which is robust to high-frequency noise and missing geometry. These correspondences are then used to drive a graph-based deformation approach. We also perform detail synthesis to help recover high-frequency details and reduce keyframe popping artifacts. Finally, we perform a motion smoothing step which improves overall temporal coherence globally. In selecting keyframes, we'll use the rationale that frames which exhibit the least similarity with other frames will introduce errors. Thus, we create a similarity score using a metric determined by the general shape of the input meshes. This is created using a combination of spherical harmonics and classical correlation. Using this correlation, we identify the least similar frames and use these to define the region boundaries for tracking. Within each region, we use an improved version of the feasibility score by Collette et al. To identify the most suitable keyframe candidate within a given region. Finally, sequential tracking is performed from the keyframe outwards to the region boundaries. With a tracking strategy identified, we move on to the sequential registration process. This process begins by creating a low-detailed abstraction of the input mesh. This abstraction reduces the impact of high-frequency noise and allows for correspondences to be driven by the general shape of the mesh. The abstraction layer is then segmented, which will support the segmentation-based alignment. The segmented abstraction of the source layer is then mapped to a corresponding abstraction of the target mesh by using a series of conditioned ICP operations. This mapping does not need to be strictly accurate and is in fact designed to identify discrepancies. Such discrepancies trigger the adaptive fusion of segments with their neighbors, which are then flagged for rigid transformation in order to preserve the detail in the source which is missing in the target. Following the segmentation transfer, non-rigid ICP iterations with correspondence pruning are performed on a segment basis for all coherent segments. We now have a set of global correspondences which are used to drive the deformation framework. The correspondences form the data constraint for a series of nonlinear equations which drive a graph-based deformation framework similar to Lee et al. This entire process is performed for every sequential mesh registration in the input sequence. The tracking region strategy introduces popping artifacts at boundaries of two keyframe regions. In order to solve this, we use a detail synthesis approach which mimics the high-frequency detail deformation of the mesh between two tracking regions. In the following illustration, we show two regions, the keyframes, and the boundary where they meet. In this example, we will show how to synthesize details between the two regions. First, we will take frame 5 and coarsely align it to frame 6, giving us 6'. We then perform a highly non-rigid surface alignment between 6' and 6, which gives us the motion decoupled surface level details from 5 to 6. This deformation between 6' and 6 is then linearly interpolated for a number of steps equal to the number of frames between the keyframe and the last frame. Using cache deformation data from the initial tracking step, the interpolated steps are propagated backwards to the corresponding frames in order to simulate a deformation and reduce jarring topology changes at the boundary. As a final global smoothing operation, we implement an adaptive 3D Kalman filter to further improve the temporal coherence of the result. In particular, this helps propagate missing motion from the geometry recovery process, which can be seen in the interpolated motion of the ball. Finally, we present our results in comparison to some of the state-of-the-art. We demonstrate the robustness of our correspondences against Guo et al., who also use a graph deformation framework driven by global ICP. We also compare to Amberg et al. As a baseline comparison with naive surface-based registration. We also demonstrate the propagation of user edits. For any given keyframe, the user may apply large topology edits which can be propagated throughout the tracking region. We thank you for your attention.